Assalamu alaikum and good morning. So previously we've looked at topic 22, one of the analytical techniques used in identifying your molecules, which was IR spectroscopy or infrared spectroscopy. Today we're going to look at the second tool in analytical techniques, which is different from the IR spectroscopy. This is now called mass spectrometry. Your learning objective is to analyze the mass spectra in terms of M over E. We call that the mass to charge values and isotopic abundances. We'll talk about the isotopic abundance shortly. You do not need to know how a mass spectrometer works, but you need to know what it is. So a mass spectrometer can be used to measure the mass of each isotope present in an element and its relative abundance. So isotopes are different atoms of the same element that contain the same number of protons and electrons, but a different number of neutrons. So for example, this is the case for, let me just open my periodic table. The simplest example that I can give you right now is carbon 12 and carbon 13. So these two are isotopes of the carbon element. Okay, there's also carbon 14, and then their quantity is the relative abundance. So which one is the more commonly found carbon isotope? Okay, so out of these isotopes, usually one of them, or maybe they would have the same relative abundances, maybe one of them would be higher than the other. Okay, so here is the simplest representation of a mass spectrum. Basically, on the x-axis, you have the mass to charge ratio. The reason why you have a mass to charge ratio is because in a mass spectrometer, your species, only the positively charged species will be detected by the detector. Okay, so if your atom or molecule is a neutral species, then it wouldn't be detected. Okay, and the charge of the atom or the molecule also affect the separation. Okay, so I'll talk about that shortly. Okay, right. Moving on to the next one. So an example of an isotopes that we can give you is chlorine. So when we talk about chlorine as the element, actually, if you look at your periodic table, the relative atomic mass of chlorine is 35.5, right? So relative atomic mass is actually the average when you take into account of the types of isotopes that are present for the chlorine element. Okay, so chlorine actually exists as chlorine 35 and chlorine 37. So if you look at this, chlorine 35 means they have 17 protons and 18 neutrons. Okay, if you look at chlorine 37, it means that they have still 17 protons because you cannot change the number of protons of an atom. The moment you change the number of protons, it changes to a different element. Okay, back to chlorine 37, the number of neutrons is 20. Okay, so I'll just write that down. Proton is equals to 17, neutron is equals to 20. Okay, whereas 35, it's proton 17 and then neutron is 18. Okay, right. So mass spectroscopy can be used to find the relative abundance of these isotopes experimentally. The relative abundance of an isotope is the proportion of one particular isotope in a mixture of isotopes found in nature. For example, when I have, say I pick out by random, okay, 100 atoms of chlorine, Cl, right? I'm talking about the atoms here, I'm not talking about the molecules. So in 100 units of my chlorine atom here, 75 of them would be the chlorine 35 and 25 of them would be chlorine 37. Okay, that's like relative abundance is just like the number, okay? But usually we talk about it in terms of percentage because it's like the probability, okay? The probability of finding chlorine 35 in a box filled with 100 chlorine atom is 75%, and then the probability of finding chlorine 37 in a box of 100 chlorine atoms is 25%. So this relative abundance is fixed, okay? In every 100 chlorine atoms, you will always have 75 chlorine 35 and 25 chlorine 37. So this is the truth about atoms actually. When we talk about atoms, they don't have only one type of isotope, okay? Some elements have even more than 2 isotopes. Now, the relative abundance is your y-axis, okay, in a mass spectrum. So you can see that here is the percentage abundance and the height of each signal, okay? So I would call this signal, represents the percentage abundance. And as mentioned earlier, the m/e is the mass to charge ratio. Usually the charge is just +1. Okay, I'll talk about that after this. This is an example. Okay, so this is an example of a boron, the element boron, which has an atomic number 5. Okay, so the mass number, there are two isotopes of boron, which is boron 10 and boron 11. Now, if you look at your periodic table, you would notice that the relative atomic mass of boron is 10.8. Okay, but there are 2 types. So this is called the relative atomic mass. I would call it an average mass between the 2 types of isotopes, but it's strictly not calculated like how you would find an average. Okay, you have to take into account of the relative abundance. So the one with the higher abundance would have a bigger contribution to this average number. Okay, so I'll teach you how to calculate how you get from the isotopic mass 10 and 11 to get your relative atomic mass, which is 10.8. That's the number you see in the periodic table, right? The peak heights show the relative abundance of the boron isotopes. So from this information, you can see that boron 11 has a higher percentage abundance. That means in nature, you are more likely 80% of the time you will find boron 11, and about 19.9, 20% of the time you will get boron 10, right? So it's already fixed. The relative abundance is already fixed. The probability is already fixed. Okay, so this is the definition of relative abundance, sometimes called isotopic abundance. It's how much of each isotope is present. That is the simplest definition we can give you of relative abundance or isotopic abundance, or just sometimes called abundance. M/E ratio is the mass to ion charge ratio. Okay, so I would just call it mass to charge ratio. For single ions, it gives the nucleon number of the isotopes. Okay, so for this first part of mass spectrometry, we're going to look at atoms first. Okay, a single atom, simple. Later on, the second part of the mass spectrometry, we're going to look at molecules, right? So in this case, the charge for a single ions is usually just +1. Okay, okay, right. So what it means by for single ions, it gives the nucleon number of the isotopes. Basically, this 10 and 11 is when you add your proton plus neutron. Okay, boron has a proton number of, well, boron will always have a proton number of 5. Okay, so that means the number of proton in boron 10 is also 5. The number of neutron in boron 11 is 6. So the only thing that's changing in an isotope is the number of neutrons, keeping the number of protons the same. How do you know the number of protons? It's the top number on your periodic table. Another name for proton number is atomic number. Moving on, this is just a basic idea of how a mass spectrometer works. So if we are carrying this out for an atom, okay, so you put in a sample of your element, okay, just choose one element, and then what happens is that your atom or element will be bombarded, will be knocked, or will be hit by a high energy electron, okay, to kick out one electron. So basically you are using an electron to remove an electron from an atom, right? The reason for this is because you want your sample to be charged. If your sample is charged, then it can get deflected and then separated, right? I'll show you in the next slide. So what happens is a sample of element is bombarded, that means is being hit by high energy electron, which can cause the molecule or the atom, since we're talking about atom, to lose an electron. So this results in the formation of a positively charged ion, and then they are separated according to their masses. Because we're talking about mass spectrometry, we want to separate the atoms that have different mass for a specific element, or we want to separate the molecules into smaller fragments, but I'll look at that in the second part of mass spectrometry. So first, you will have to introduce your element, usually in the form of atoms, okay, where you put in the starting place of the mass spectrometer, okay, and then atoms which would be neutral initially will then be bombarded with this high energy electron so that it forms an ion. Okay, it's a positive ion because you always knock out electron from the atom. So once you form an ion, okay, they will pass through this electric field. There will also be some magnetic field in this machine, but you don't have to worry about that. So what happens is that the stream of ions is brought to a detector after being deflected by a strong magnetic field. So the reason why you want this deflection to happen is so that this happens, okay? If I introduce neon atom, okay, neon element, say I introduce 100 neon atoms, okay? Out of this 100 neon atoms, some will be 20 neon 20, some will be neon 21, and some will be neon 22, okay? And then when I take the sort of average, okay, of these 3 atoms, I should get a neon with a relative atomic mass of 20.2. So this 20.2 is the number that you see in your periodic table. Okay, actually, the isotopic mass of neon is 20, 21, and 22. That means since neon has an atomic number or proton number of 10, neon 20 contains 10 neutrons, neon 21 contains 11 neutrons, and neon 22 contains 12 neutrons. So these are the 3 isotopes of neutrons. And we need that deflection so that they can be separated. And then what happens at the detector is then the detector counts how many neon 20 is hitting the detector, how many neon 21 and neon 22 is hitting the detectors, and they come out as relative abundance. Okay. So the detector is connected to a computer which displays the mass spectrum. So that's when the mass spectrum is being produced. Another thing that I want you to notice is this angle of deflection. I think I have mentioned this earlier in either topic 1 or topic 2, okay? So when we talk about the angle of deflection, usually the lighter species, in this case, the lighter isotope, will get deflected more. You can see that the angle of deflection. How do you what is the baseline of this angle of deflection is that I'll use a purple line, okay? So you take because the stream of neon ions initially was a straight line, right? And then once it reaches the magnetic field, it then gets bent. Okay, so that is your straight line. It's not supposed to be there. I'll put it at the bottom. There. Okay, so you can see if this straight line is your baseline, you want to see how far the angle of deflection is. Okay, so you can see that the black root has the smallest angle, so we say that it gets deflected less. Whereas the red root, if you compare it to the baseline, which is the purple line, the angle is the biggest. So biggest angle of deflection means it has the biggest deflection. So that means it deviates the biggest from your baseline. Okay, if there was no deflection, we would expect we would expect them to continue traveling in a straight line, right? But because of the magnetic field and because they have different masses, they are deflected at different angle. And what you need to conclude from here is that the lighter the mass, the more it gets deflected. The heavier the mass, the less it gets deflected. Okay, so then how does the mass spectrum show? The computer will then plot the graph, and it looks like neon 20 is the most abundant isotope of neon. Okay, but we cannot just say, oh, because only 0.26% of neon 21 exists, we're just going to leave that out. No, we have to take into account, okay, 90.92% of neon 20, 0.26% of neon 21, and 8.82% of neon 22. So when you do the calculation to find relative atomic mass, they would come out as 20.2. Okay, so I'll teach you the calculation. We're almost there. Okay, so abundance can be seen as number of atoms. So you just imagine out of 100 neon atoms, 90.92 of it will be neon 20. 0.26, that's a little bit lower than 1. Well, very, very low, very, very low than 1 will be neon 21, and 8.82 will be neon 22. Okay, so that's why I talk about probability, because if we were to talk about the number of atoms, these are in decimal places. Okay, so the highest of the peaks represent the abundance number of the height of the peaks represent abundance number of peaks of that isotope. Okay, so I've already talked to you. Now, you would sometimes see the label M over Z, okay, which means the same, mass to charge ratio. M over E or M over Z is the same. Basically, it's just the mass. It's telling you the mass, okay, 20, 21, 22. Okay, now we next want to calculate the relative atomic mass of an element given the relative abundances of its isotopes or given its mass spectrum. So you need to be able to analyze the mass spectrum. So how do we determine the AR? AR here, we're talking about the relative atomic mass from mass spectra, okay? There is a formula that we use to find the AR of an element, okay? You take the abundance times by the mass of each isotope, okay? So for example, just now, my neon is neon 20 has a relative abundance of 90.92%. So I take 90.92% of neon 20 plus 0.26% of neon 21 times 21 plus 8.82% times 22, and I add them all up together. So I should get the relative atomic mass if I do that, okay? So let's see. Oxygen. So there are actually 3 isotopes of oxygen. Oxygen 16, oxygen 17, and oxygen 18. Now, which one is the most common one? You look at the percentage abundance, okay? That's why we are only familiar with oxygen 16, but actually there can be oxygen 17 and 18 as well, okay? It's just that they're present at a very, very, very low amount. So what happens? What is the relative atomic mass of oxygen? Okay, so to find the relative atomic mass of oxygen, which is the AR, okay, you need to take the isotopic mass. And the isotopic mass is the numbers of protons plus neutrons, okay? So isotopic mass is this 16, 17, and 18, and it can be thought as proton plus neutron, okay? So you take the abundance of each isotope, right? So I'm going to convert it into 100%, okay? Percentage abundance. Sorry, I'm going to convert it into percentage. So first, we take 99.76% times by isotopic mass 16 plus 0.04% times isotopic mass 17 plus 0.20% times isotopic 18. Okay, so that means we take into account of the oxygen 16 isotope, and then we also take into account of the oxygen 17 isotope, and lastly we take into account of the oxygen 18 isotope, and the total of the percentage abundance should be 100%. Okay, sometimes you will see another version where they like to combine. Okay, so you can see, well, they are both the same actually. So you take 99.76 times 16 plus 0.04, oops, times 17 plus 0.20 times 18. Make sure they're all in bracket, especially when you put these numbers into your calculator, over 100. So that's the same thing. Okay, whether you want to do individual percentage times individual isotope, or you take the overall over 100, right? Can you please work that out and give me the answer, because AR is usually to 1 decimal place. So give me the answer to 1 decimal place. All right, so I'll leave you to work that out yourself. And I will move on to the next question, okay? What if this time you are given the mass spectrum of zirconium ZR? So zirconium, let me have a look at zirconium ZR, which is about, where is zirconium? Okay, so zirconium is in group 4 of your transition metals, okay? So it has an atomic number of 40 and the relative atomic mass is 91.2. So zirconium has 1, 2, 3, 4, 5 isotopes, all right? Isotope 90, zirconium 90, zirconium 91, zirconium 92, zirconium 94, and zirconium 96. Okay, so from this graph alone, we can conclude that zirconium has 5 isotopes. Cannot spell. They are zirconium 90, zirconium 91, zirconium 92, zirconium 94, and lastly zirconium 96. And the most common zirconium isotope is zirconium 90. Okay, so this is the most common because it has the highest relative abundance. All right, so the number you see is the relative abundance: 51.5, 11.2, 17.1, 17.4, and 2.8. So to find the AR of zirconium, you deal with each isotope at a time, okay? So I will start with 51.5% of zirconium 90 plus 11.2% of zirconium 91 plus 17.1% of zirconium 92 plus 17.4% of zirconium 94, and lastly 2.8% of zirconium 96. So you should get a number again to 1 decimal place. You just have to make sure that the total abundance is equals to 100. Okay, check that 51.5 plus 11.2 plus 17.1 plus 17.4 plus 22.8 is equals to 100. So just remember sum of relative abundance is equals to 100%. Okay, if they give you the relative abundance in fraction, sometimes they do this, the total or the sum of relative abundance should be equals to 1. Okay, right. So that's how you use the formula. Okay, if you want me to label, this is the first one is of zirconium 90. This is zirconium 91, zirconium 92, zirconium 94, And lastly, zirconium 96. Now, how do you check if your answer, your calculation is correct or not? Check your answer. Does it match with the value AR in the periodic table? Okay. Work out your calculation and check if your calculation is equals to 91.2 for zirconium or something close to that number. That means you're on the right track. If you get a number that is far off, like 120, for example, that means there's something wrong with your calculation, okay? Your AR calculation must be similar to or close to the value of AR in the periodic table. You have access to the periodic table, so you can always use that, okay? Right. Next, we move on to the next part of the mass spectrometer. Okay, so this time we want to deduce the molecular mass of an organic molecule from the molecular ion peak in a mass spectrum. Okay, 4 suggests the identity of molecules formed by simple fragmentation in a given mass spectrum, right? Okay, so again, the same idea is applied when we look at the mass spectrometer of molecules. There will be high energy electrons that will bombard our molecules. So two things can happen. One, the electrons is being removed from our molecule, or our molecules can be broken down into what we call fragments, right? So these high energy electrons will knock electrons out from, will knock electron out. So usually we just knock out one electron from the molecule, and it can also break the covalent bond of the molecule to form smaller pieces, which is called the fragments, or we call this fragmenting. So when organic molecules are passed through a mass spectrometer, it detects both the whole molecule as a whole, but as long as it's positively charged, okay? And it can also detect the fragments, the broken pieces, again, as long as it's positively charged. Okay, so mass spectrometer can be used to find the isotopic mass, the one that we just did just now. And it can also be used for not only for atoms and isotopes, but it can also be used for molecules. Okay, the main use of mass spectrometry is in identification of organic compounds. Now, first, I would like to introduce to you the term molecular ion, M+. Okay, so the word there is a molecule, but it becomes ion. So what is a molecular ion? A molecular ion is when your original molecule has lost one electron. How does it lose electron? From this bombardment of high energy electron. Okay, so basically just imagine there's a gun that shoots out electron to remove or to kick out one electron from the molecule. Okay, so the molecule has not been fragmented. That means the molecule stays intact. Nothing is being broken. The only thing is that you just remove one electron from the molecule. Okay, how do you identify this molecular ion in your mass spectrum? It is usually the peak with the highest mass to charge ratio. And usually the charge is just +1. As I said, we are only removing one electron so that the charge becomes +1. And if you take mass to charge, okay, if your mass is over 1, which is your charge +1, then essentially mass to charge ratio is just your mass really, okay? So it is the highest peak, the biggest mass to charge ratio in your mass spectrum. So this is, I've got a mass spectrum here. I don't know who it belongs to. Okay, same thing. I've got a relative abundance. I've got mass to charge ratio here. Okay, the only difference is now I am talking about molecules, so I have to take the mass of the whole molecule. I add up the mass of each atoms. Okay, so the molecular ion is usually the peak with the highest mass to charge ratio. It's not the highest peak. Okay, it's not that one. That is a fragmentation. That is a small parts of your molecule. The highest peak, the peak with the highest mass to charge ratio is, I have to look at the axis and the one that has the biggest mass, which is here around 58. So that means my molecule has a charge, my molecule has a mass of 58. All right, so I have to read off the x-axis. So please don't get this confused. Okay, so students always think, oh, this is the highest peak. Sorry, the peak with the highest relative abundance. But the molecular ion is usually the last, the signal that has the biggest number on the x-axis, or the peak with the biggest number on the x-axis. Okay. What happens? All right. So what happens during this molecular ion fragmentation is that there is no fragmentation happening. Okay, you are only just removing one electron from the molecules. Now we're going to look at example 1, which is the mass spectrum of a propanone, CH3CO CH3. Okay, so so this is actually the mass spectrum of a propanone. Right, so I'm going to show you what happens at this peak, 58. So what happens is that your CH3, CH3 is being bombarded by high energy electrons to become still CH3, CH3, except that it has a charge of +1. So if you count the total, the AR of each CH3, CH3, taking your carbon as carbon 12, hydrogen 1, oxygen 16, you should get a total of 58. And that represents your molecular ion. Okay, so just label this. 58 is your molecular ion, which is called the M+. The symbol for molecular ion is M+. And this is represented by CH3CO CH3 plus. Okay, I'll talk about the smaller, the other fragments here. You've got fragmentation at the mass 43. You've also got a fragmentation at the mass of 15. So I will show you what fragment represent this peak, or what fragment is producing this signal shortly. Okay. Okay, so we're going to address the other peaks now at 43 and 15. Sometimes in a mass spectrum, there will be a lot of peaks, a lot of signals, and you don't necessarily have to identify each of them. Okay, so you just identify the, I would say the significant ones, okay, or the common ones. All right, so what happens when you introduce propanone into your mass spectrometer? There are many things that can happen. Okay, the first one is the formation of the molecular ion. It's basically just molecule that has been removed one of its electrons to form a cation. Okay, so this is just the formation of molecular ion. The second thing that can happen is called fragmentation. So fragmentation usually happens by breaking the covalent bond, either the carbon-carbon bond, okay, or some other common bonds being broken is carbon-oxygen or carbon-nitrogen, okay? But the most common one is carbon-carbon, right? So what happens is that the high energy electron that comes from inside the mass spectrometer can either break this bond, okay, in which case you get fragments of CH3 radical, that's neutral, okay, plus COCH3 plus ion, right? So you always have neutral and cation. Okay, so that's one of the possible fragmentation. The second possible fragmentation is also at this bond. We're breaking this bond, but instead of getting the CH3CO cation, we now get the CH3 plus cation, and then the CH3CO radical neutral. Okay, so you cannot get, hold on, you cannot get both CH3 plus and CH3CO plus at the same time. They have to happen at different process. Okay, so here you've got a CH3CO plus cation. In a different process, you've got a CH3 plus cation. Now, if we count the mass, okay, 12 times 2, 24, 24 plus 16. I have to use the calculator because I know I'll make a mistake. 40 plus 3 hydrogen is 43. Okay, so how do I do that? I'll just show you quickly. 12 plus 2, since there are 2 carbons, plus 16 plus 3 is equals to 43. So that means, you see the peak, the signal at 43. This signal is caused by the CH3CO plus. Well, it doesn't matter where you put the plus sign, okay? Or sometimes that, it's also fine, okay? Next, you look at the other. So remember, only the charged species will produce a signal, okay? So only cations will be detected by mass spectrometer, which means cations will produce signals. Your neutral fragments will not produce any signal, plus it will not be detected by the mass spectrometer. It will just be flying around or just staying around in the machine. Okay, next there is another positively charged fragment, which is your CH3, and if we count the mass for that, that's simpler to count. We've got carbon 12 plus 3 hydrogen, so we've got 15. Okay, if you look at the graph, you see a signal at 15, and that is caused by your CH3 plus fragment, okay, or you can write it as CH3 plus. So you have to look at the structure and to break the correct covalent bond in order to get fragments. You don't just get fragments simply by breaking any bond or you know, just choosing some smaller number or smaller mass. They have to make sense, okay? They have to come from the propanol. They have to come from the molecule. So these are the two things that can happen in a mass spectrometer. Okay, first you get the formation of the molecular ion. Maybe I should label this formation of molecular ion. And you will always get the formation of molecular ion because otherwise you will not know the mass of this molecule that you introduce, M plus. The symbol for molecular ion is M plus, okay? And the M plus is always the last peak or the biggest peak in the x-axis. That tells you the MR. Well, it sort of tells you the MR of the molecule, okay? So in words, I have explained it to you in words. I'm not sure if that was in your notes, but if we just go through quickly this explanation, the peak at the highest mass to charge ratio is caused by the molecular ion M plus. So we're talking about this here, okay? This is formed by the sample molecule being bombarded with the high energy electrons and one electron is being knocked out. So basically the molecular ion just give you the relative molecular mass. So that's what I was talking about. It is the MR of the molecule. There are large peaks at 15 and 43 due to fragments produced when propanol molecules are broken apart by electron bombardment. So the peak at 15 is caused by the CH3 plus fragment, and the peak at 43 is caused by the CH3CO fragment. Yep, okay, correct. CH3CO plus. Make sure you don't forget the plus sign. Okay, so if you want to copy this down, you can. I'll leave it there. I'm not sure if you can see it. Otherwise, I think that's the best that I can do. Okay. All right, if you want to copy this down, you can pause it. I'm going to have a look at the next example. Oh, before we look at the next example, I just want to point this out. The breaking of single bonds such as carbon-carbon, carbon-oxygen, or carbon-nitrogen is the most common cause of fragmentation. So remember, we only break the single bonds during fragmentation in a mass spectrometer, okay? So this is just a model diagram showing you that you will start from a molecule or a molecule plus, and then you fragment them, whether you break it between the C and U of molecule, or you can break it at between O and L of the molecule, or between E and C of the molecule. Okay, it's such a bad example. It's such a bad diagram because I would rather use a molecule, an actual molecule with actual formula to show the fragmentations. Okay, now this is the second example of a mass spectrum of propan-1-ol CH3 COCH3. Okay, just now we were looking at that's not right, is it? Because that is not the formula of a propan-1-ol. It's, I must have copied and pasted it. Okay, change the formula of propan-1-ol to CH3, CH3, CH2, CH2OH. Okay, so that's C3H7, something's wrong. Ah, correct. C3H7OH, yeah. Okay, so if I were to draw this out, propan-1-ol means it's on the first carbon. Okay, so I've decided to draw my first carbon on the right. Okay, first thing to notice is the molecular ion, okay, which is the biggest peak on the x-axis, or the peak with the highest mass to charge ratio, 60, yeah? My suspect is that is our molecular ion, M plus. Let's see if we take the MR of propanol, propan-1-ol, 12 times 3 plus, we've got 7 hydrogen plus 16 plus 1, 60, yes. The MR is 60. That means the signal at 60 is caused by CH3, CH2, CH2OH plus. Do not forget your plus charge. All right. So you can see there are a lot of peaks, a lot of signals, but usually we just identify the signals that are labeled with numbers, or sometimes the question will tell you which one to identify. If there is no label for the other signals, leave it. Do not stress yourself out. Okay. There will be a lot of peaks, a lot of signals that sometimes it's just irrelevant. Okay. Let's see. Okay, so we start at 59. That means I have lost one hydrogen. Yeah. Okay. And how do I know that? Because 60 minus 59, that's just 1 unit. And what's 1 unit that can be lost from the molecular ion, right? So it's just losing the hydrogen. That means 59 is caused by, remember, your fragments have to come from the original molecule. So don't try to make up the fragment. CH3, CH2, CH2O plus. Okay, so that means you have just lost one hydrogen. Next, what can we do? Maybe we start fragmenting here. Imagine there is a fragmentation happening here. Okay, so you can either get CH3, CH2 plus in one reaction, in one fragmentation, and another separate different fragmentation, you can get CH2OH plus. Okay, so if we take CH3, CH2 plus, that would be 12 times 2, 24, plus 5, 29. Okay, so 29, the signal at 29 is produced by CH3, CH2 plus. Everyone agree with that? Next is CH2OH. So that's 12 plus 16, which is 28 plus 3 hydrogen, 31. Okay, so that is caused by CH2OH plus. Okay, I like to write the plus where near the bond that is being broken. Okay, 42. 42 is an interesting one. So you have to find fragment that represents a mass of 42. My guess is it involves 3 carbon, because 3 carbon is 36. That's the closest to 42. So I've got 2, 4, 6. Okay. Now 42 is a bit of it's not as quite straightforward, okay, because 42 involves the loss of water, right? So if we lose water from alcohol, that means we lose OH here, and then we lose the hydrogen here to form an alkene. Okay, so this can happen as well, right? So that means 42 is caused by CH3, CH2. I need 6. 36 plus 6 is 42. 3 plus 2, 5, and CH2, CH. Is that correct? Oh, no, no. It should be CH and another CH. Okay, so this one I can just put, that doesn't work out. CH2, sorry. Okay, so this one is a special case, loss of water. So you lose water, and also you fragment, it produces fragmentation so that it becomes a positive ion. Otherwise, if you just lose water from an alcohol, you will get a neutral alkene, right? You wouldn't get an alkene with a positive charge. So some sort of fragmentation is involved here in order to form the positive charge of an alkene. So 42 is not that easy to spot out, all right? So that's how you analyze your mass spectrum and try to identify which fragment is producing which signal, okay? And then you may ask, what happens if I break the molecule here? Of course, that can happen too. What's that? 12 times 2 plus 5 plus 16. 45, is that correct? If I break it here, I've got a fragment at 15 and 24. 1, 2, 3, 4, 5. 29 plus 16, 45. Yeah. So you should be seeing a fragment at 45 there, somewhere there, and a fragment at 15 is not shown. Okay, it's missing there. So it doesn't matter. All right, you just have to identify what can be identified and what the question requires, really. Okay, so that's that. High resolution mass spectra. Okay, so high resolution mass spectra is self-explanatory. This actually, there's no learning objective for this part, but it was mentioned in your textbook, so I thought, I'll just talk about it once, right? High resolution mass spectrometers can distinguish between ions that appear to have the same mass on a low resolution mass spectrum. So low resolution mass spectrum is the one that gives out the mass to charge ratio to like nice whole numbers. Okay, like for hydrogen, it's 1, carbon, it's 12, nitrogen is just 14, but in a high resolution, nitrogen is actually 14.0030738. And oxygen in a low resolution mass, we use 16, but actually in a high resolution mass spectrometer is 15.99499141. Okay, so what is the importance of this high resolution mass spectrometer is because it can differentiate between two molecules or two molecular ions that have the same mass in a low spec, right? For example, C2H7N and CH3NO. In a low spec mass spectrometer, the molecular ion would produce a peak at 45. Okay, so we're not able to differentiate them because they both have the same number and would form the same signal at the same mass to charge value. Okay, however, in a high spec, C2H7N would produce 45.057846, whereas CH3NO would produce a peak at 45.021462. That is all. That the high spec mass spectrometer, high resolution mass spectrometer can differentiate between molecular ions that have the same mass to charge ratio at low resolution mass spec. Okay, otherwise you don't have to worry about that. Okay, so I will stop here because the next one will be the M+1 peak, and that's a longer section, and I don't want to have to stop in the middle of this section. Okay, Assalamu alaikum, and thank you, everyone.